Hello, students. Today, what we want to do is to discuss section 1.1 on linear equations. You'll find a lot of the material that we discuss in this lecture is review, but it's very important. And also, we will touch on some equations that will render a linear form once we clear denominators. That's often called the LCD method, and I would like to review that. So let's go ahead and get started. I'll share my screen. Now, one thing that we'll spend a lot of time on initially will be certain types of equations. And one that we will study also this week will be the quadratic. But when it comes to the linear equation, it has a very simple form. And I'll just use uppercase since we're going to use lowercase for the quadratic. So we would have ax plus b equals 0. And it really doesn't matter where the a and the b live. They can be any number. So we'll just say a and b are constants. Now, for instance, we have a lot of notation that we use in mathematics. So if we wanted to say they were real numbers, we can use what we call a script R to denote real numbers. That's a common notation when you're writing and you don't have a boldface. When we type, we can bold anything, but that's like a boldface R when you're writing it, or if I'm writing on the board. And so we could say that A, B contained in R, real numbers, are fixed. And when we say a particular letter or representation of some type of number is fixed, we mean it's constant. So when you fix something, it's constant, it does not vary. And this will be a terminology that we use as we go through our pre-calculus courses and then on into calculus. So let's start with some very simple examples. I'm just going to go to our lecture notes and pick some of these good examples. So one that we have, and let me show you where I get this so you'll be knowledgeable of that. When you go to Blackboard, we have some really nice problem sets that come with our Pearson Learning, and these will exemplify the types of examples and problems that you will need to master as you work through these sections. So the very first one that I chose was 1C. So let me go ahead and write that down, and then I'll share my screen. So if you like, you can go ahead and write this problem down. So we have x plus 4 divided by 2 plus x plus 1 divided by 3 equals 10. And in all of these cases, what we want to do is solve for the variable. So I'll go back to my screen with the document cam. So when you look at problems like this, you go back up to the original form of a linear equation, and you see that we don't have just one term that has x, and we don't have one term that's a constant. We do, and we don't even have the 0. So the idea is that with linear equations, we have a little bit more flexibility. So when you think about solving a linear equation, the first thing that comes to mind is solving for x or isolating the x. Now, one thing I want to go over is what we call the least common denominator method. Now, notice, of course, 10 has a denominator of 1, so I'm just going to go ahead and write that in. But when we look at the other terms, we have a denominator of 2 and a denominator of 3. So we can say least common multiple will include a 2 and a 3. It also includes the 1, but we know 1 is the multiplicative identity, so we don't really need to write it here. So a simple, very, very simple way to clear the denominators is to do it symbolically. So notice I did not multiply these two numbers. I want to keep them separate so you can see as the terms absorb. A lot of times in your previous classes, you may have used the word cancel, but I'm not going to use that. I'm going to show how the particular numbers absorb, and I'm not going to put slash lines through them. I'll put boxes around them so you can still see them. So here we have x plus 4. So we're going to write the equation again, plus x plus 1 over 3. And then you can use parentheses or brackets, and then you're going to have 2 times 3 as a multiple here. Do the same thing for the 10. Use brackets or parentheses, and you have 2 times 3. Now, if you like, you can put that in parentheses just to show multiplication. So now what we want to do is absorb the common terms. So now, and we can do this symbolically without having to overwrite. So now when we multiply here, we see that the 2's absorb each other, and we're left with the 3 and the x, the 3 and the x plus 4. But notice this is 3 times x plus 4. So equivalently, and of course, all of these are equivalent. So I'll just write this here too. The double arrow just means equivalent, go in either direction. The 2's absorb, and we have 3 times x plus 4. Now we look here at the second term and the least common multiple, and we see that the 3's absorb. So the 3's go away, but we're left with 2 times an x plus 1. So we have the 2 factor and the x plus 1. The main thing that we want to remember is that when we're multiplying, we always have to use the distributive law. So be sure to remind yourself that these multiply. They're little teaching notes in the lecture notes that say, remind your students of these items so that they don't make careless mistakes. And don't worry about making mistakes. If you practice enough, you'll be confident when you take the test. Now, on the other side, we look at this and say, well, there's really not a whole lot here. We've got a 3 here, we've got a 2 here, and we don't really have common multiples in any of these that could be absorbed throughout the equation. So we can just go ahead and say that 2 times 3 is 6, and 6 times 10 is 60. So we're not seeing any terms in the equation that can be absorbed. So now we just go ahead and multiply and collect terms and have a goal of the original equation up here. And if you like, most of us will just decide to move the b over because that makes it easy since linear equations are so simple. So now equivalently, we have 3x plus 12 plus 2x plus 2 equals 60. So now it's starting to look a lot simpler. Now we can add like terms. The 3x plus the 2x is 5x. And of course, 2 plus 12 is 14. And we get a 60. So now we're thinking, do we want to go directly to this form? Well, not really. Since the equation is so simple, it may be just easier to go ahead and subtract the 14 from the 60 and make it a little bit easier since the equation is simple. So of course, 10 from 60 is 50, and subtract another 4. That gives us a 46. So 5x is equal to 46. And then, of course, at this point, we can simply divide by 5 and solve for x. And there are no common factors here. They're relatively prime. So we get 46 divided by 5. Now, what we notice about the original equation is that there are no real numbers for which it is undefined, in the sense that there is no way to substitute an x that would render the equation undefined. What we do know is that because of the simplicity of the equation, it's not a surprise at all that we have one unique solution. Now, again, when we solve problems that have linear form or that are reducible to linear form, we just want to make sure that when we isolate a value of X, that it makes sense. Now, we don't have to worry about this not working, because certainly when we supply the X equal 46/5, this will certainly make sense. Now, I will only look for issues where the equation is rendered undefined. You are certainly welcome to go back and check your answer, but I am more vigilant about working the problem correctly and then ascertaining that this X is a value that solves this equation. Number one, because we have isolated the X, and number two, it would certainly make this equation well defined. So what we can do here, just so you can get used to using set notation, you can also say that 46/5 is the solution set. So often what we want to do is say that, okay, X has a particular value, but then we go to the next step to say, okay, this is actually a solution to this equation, okay? So remember, linear equations, the most easy way to spot them is that you have first degree in the variable. And of course, X is a popular variable, but you know from your science classes, you can use T's, you can use Z's, Y's. It doesn't matter what this variable is. And what we can do, as you see here, is basically reduce our given equation to this form. Now, notice here, like I say, we didn't create the zero because it wasn't necessary to do so. Later on, we may be a little bit more particular about this when we're working with quadratics. But again, certainly give yourself a break by just going ahead and isolating the X term and then dividing, as opposed to actually going to this form. But even if you do it, there's no problem. It's still legitimate mathematically. Okay, let's try another one. Now what I want to do is look at one of the examples from the lecture notes that looks a little bit different. And this one is the following. That is, we have 1/4. You can see these on the lecture notes. I won't pan back to that to save a little bit of time. And then we have 6/x equals 5 divided by 8. Now, many times when you're working a math problem, the first thing you want to do is to know what is the question being asked. So when we look at these, what we're saying is solve the equation. Now, when we solve the equation, especially with linear, we're basically trying to isolate the X. And like I said before, we will tend to see most variables being real numbers, or if we're working with quadratics where we may venture into the imaginary, we're probably only going to see, at least for the time being, real coefficients, real numbers. Like maybe you have a fraction here, 5/8, and then of course you've got a 6 in the numerator. We may end up with some radicals and things like that. But the idea is when we solve an equation, we may sometimes be asked to solve in a particular number system, or the equation just says, or the directions just say solve, and whatever we get is what we get. So in this particular case, what we want to do is clear the denominator. So let me write that down in red, so it's clear, no pun intended, right? Clear the denominators. Now, this may be something you've done a lot of before, and that's fine, but please don't look at this as being not worth your time. The more you practice, the more you work with these types of equations and hone your skills, the better off you're going to be. Because what you'll eventually start doing is you'll be able to have more confidence as you work, and your work will be neat and orderly. Now what we want to do is look at the denominators. Notice here, the 8 is just a 2 times a 4. So I'm going to rewrite the equation so it's really clear what all the factors are in the denominators. Now, you don't have to do this, but for instance, imagine that you were showing someone how to do this problem and you wanted to do it the easiest way possible. So now when we look at the equation, what do we have in the denominators? Well, we need a least common denominator. Firstly, we need a 4. So we've got a 4 factor. Then we need an x. And now we already have a 4. We don't need 2 copies of 4. I mean, that's not a 4 squared there. So we've got the 4, but we don't have the 2. Now, what I'm going to do is I'm going to put the 4 times the 2 first and then the x. Now, I'm kind of overdoing the little dots for multiplication. I'm just spreading them out so you can see the individual factors. So it's easy to see which terms absorb when you multiply through by the least common denominator. Now, what's important at this stage of the problem is, like I was saying before, remember in the previous problem, we had denominators of 2 and 3. Here we have a variable in the denominator. That is, we have an x. Now, clearly, we know that if x were to assume the value of 0, then the equation would not be well defined. We'd say the equation is undefined because division by 0 is not something we understand. So what we would do here is solve the equation and then make sure that none of the values of x that we would obtain would be 0. Now, of course, you pretty much can see that we will probably get a non-zero value for x, but what we want to do is just explicitly state that x cannot be 0. And even though that's maybe easily assumed or obvious, we want to share this with the person that we may be teaching, that this value of x would never be acceptable as a solution. So now we've got that. We're kind of keeping that in the background just to make sure that we don't mow over it if it happens to occur. Now what we want to do is multiply the equation by the LCD. I'm going to use the same formula or same format that I did before. So you can use parentheses or brackets. I'll go between the two. It doesn't really matter. And then we have 4 times 2 times an x. And here we have 5 divided by 4 times 2. And then, of course, we can use more brackets if you want, your choice. Just make sure it's clear what you're doing. So just to be parallel to the other side, we'll do that. Now, what we can do is, again, another symbolic calculation. When we think of the distributive law, we have, just like we did on the last problem, we have to multiply the LCD by 1/4 and the LCD by the term 6 over x. But when we compare the two, we see that the 4 is absorbed and the 2x is left behind. So again, equivalently, we get a 2x. And now when we compare here, we see the x is absorbing. You don't have to put slash lines through things. And notice I'm not using any boxes right now because again, as I go between the two terms here, different values will absorb, or different factors will absorb. So you don't have to do that either. And certainly don't multiply all of this out and have extra terms when you can easily do it symbolically. So now the x's are gone and we're left with a 4 times a 2, which is an 8, times a 6. So I'll go ahead and write that out, 8 times 6. So again, the x is absorbed. We're left with the 6 times the 2 times the 4, or we have 8 times 6. Now on the other side, we see that the 4 times the 2 absorbs. So that way, if you basically break down all the numbers, you don't have any guesswork to do. A lot of times we won't be as fastidious, but if we look at how the numbers break down, we can easily see which factors are absorbed and which are left behind. So notice the 4 times the 2, they go away, and we're left with the 5 times the x, or a 5x. So now it's actually very simple. Now at this point, you're thinking, does it really matter, where I put the x? Of course not. Doesn't matter at all. So we can transpose. We can basically just subtract 2x from both sides. And we have, in this case, 8 times a 4, excuse me, 8 times a 6, that's just a 48. And then we have a 3x, 2x from 5x. Now, if you like, we can just go ahead and write this. If you wanted to do a factor tree, this is just 3 times 16. Now, I can give you an example where you could do boxes if you wanted. You can see now on opposite sides of the equation that the 3's in this case will absorb. And so now you're left with x equals 16. So we have x equals 16. Now, one thing that's interesting about this particular problem is if we compare it to the last one, we're still good. That is, 16 is not equal to 0. So this will imply that we have a legitimate solution. So we could put that in the solution sets. So again, we have a solution set that contains one element. This equation has a unique solution. Now again, the symbolic calculation that we're doing to show how factors absorb makes the process very streamlined. And you can always go back and compare and check your work very easily because all of the numbers are broken down. And then you can continue to factor and see that on opposite sides of the equation, these two terms absorb, or like you say, you can say cancel. But it's always a better technique just to put boxes, okay? Don't use slash lines. I know that's a very popular technique, but it clutters the work and then you can't see anything. You've put a mark through it. So don't use that technique. And now you can see that you have x equals 16 is legitimate because it's clearly not 0. So the LCD technique is really nice. We'll use this over and over in mathematics. And a very, very worthwhile technique. Now, what I have here, I've just got a, let's try another LCD method, and then I'll go back and just do a distributive law. Again, these types of problems are not overly difficult. You're going to be reviewing distributive law. You're going to be reviewing solving basic equations, lots of very fundamental approaches. And what we want to do is get better. We want to improve our techniques. So here's another example. Say we have 5 divided by x minus 2. And this equals -3 divided by x plus 2 plus 28 divided by x minus 2 times x plus 2. So when you look at this problem, and again, what we want to do is solve the equation. The idea again is if we look at this problem, we think that the original problem is user-friendly, so to speak. Notice here we just have a factor difference of 2 squares. That's a very fundamental identity in algebra we use all the time. And we'll say more about that when we talk about quadratics. And so instead of this being x squared minus 4, just notice, I'll just say observe. This is, like I say, a fundamental identity. We know that x squared minus 4 equals x minus 2 times x plus 2. And that fundamental identity, well, we could just write it as, we can use A's if you want to represent any particular expression, if you like. A squared minus b squared is a minus b times a plus b. So that would be what we call an identity, an equation that's true for all values of the variables for which it is defined. And so you learned this back in Algebra 1. So what we're seeing is that we have the factor difference of two squares here that really makes the problem easier. If it weren't factored, we would go ahead and factor it so we could see what types of particular factors we have in the denominators. Now we can go through and write down our LCD. So it doesn't matter. You can start over here and move this way, whichever way, it doesn't matter. So we need an x minus 2. That's the first factor we need. If we move to the second term, we see we need an x plus 2. And then when we get to the last term here, we don't have to worry about anything. I mean, we've already got the x minus 2 and we already have the x plus 2, so we're good. This is our LCD. So it doesn't matter if we just have factors from a difference of squares, or if we have factors from factoring integers using the fundamental theorem of arithmetic. It's the same thing. Remember, the variables represent numbers. So they work just like numbers. All of the properties that we deal with when we talk about integers, we transfer that to the real numbers. And then, of course, we add some really nice things like multiplicative inverses because we have multiplication. So now let's go ahead and multiply by the LCD. I'll go ahead and write this first. It doesn't matter what order you do this. So we're going to multiply the term on the left by the LCD. And we'll do the same here. Again, this is done symbolically. It saves us a little time, and then it allows us a good way to go back and check the work. So we have minus 3 over x plus 2 and plus 28 divided by x minus 2 times x plus 2. So when we look at this, we're at the same place as we were in the previous problems. Notice here on the left, the x minus 2 is absorbed, and we're left with 5 times x plus 2. Now, of course, you can put as many steps as you like into your work. You can leave out steps. Put as many steps as you need to show a clear, logical flow. But I would say more steps are probably better so you can check your work. Now, if we look at the term here to the right of the equal sign, we see the x plus 2 is absorbed, and we're left with the negative 3 and the x minus 2. Remember, distributive law. Do not forget negatives. They get dragged along. If you leave out a sign or you forget the distributive law, that really does change the problem. And now for the last term, we see that everything goes in the denominator. The x minus 2 and x plus 2 absorb, and we're just left with the 28. So that was really simple. The idea is if you use the symbolic calculation here, it gives you a very simple way to show which terms absorb. And let me now just kind of go back and say why I was mentioning equations reducible to linear form. Notice we start here, but the reduced equation is indeed linear. We could collect all the x's and collect all of the constants and have the ax plus b equals 0, standard form. So the key here is that when we clear the denominators, we result in an equation that is linear. Now, of course, you might be thinking, if we clear denominators, maybe we end up with another type of equation. Maybe it has powers of 3 in it. Maybe it has squares in it. It's quadratic. It really depends on the nature of the given equation. Now, what's interesting about this technique is that we use it quite a bit. And as we learn more functions and we work with different types of expressions, we will still apply these techniques. So they are quite fundamental. So now let's go ahead and multiply. So we get a 5x, and a 5 times a 2 is a 10. Very simple, but very important. And then we have a negative 3x. And of course, the additive inverse times the additive inverse is the positive. That absorbs. That's something we could actually prove. You should think about that. Why is the negative times the negative? Why do those terms just absorb each other? Why does that become the positive? That is actually a theorem. You should think about that. And if you would like to say more about it, we can talk about it during conference hours. So now we're really getting into some very simple equations here. Now, at this point, this is completely up to you. If you like, we can go ahead and add the 3x to both sides and get a 3 plus a 5, which is an 8x plus a 10. And then, of course, we could add the 6 and the 28 to get a 34. Again, like I said before, since the linear equations are so simple, what we tend to do is put the constant on one side and the variable on the other because it's just a simple equation. You could still factor things on one side and still get the solution. And I'll say something about that in a minute. But if we keep the same procedure we've done now, we can subtract the 10, and that'll give us a 24. And then we have 8x. And then, of course, 24 is just 3 times 8, right? So now, of course, the 8's absorbed. And we get x equals 3. Or we're told that x equals 3 is a result of what we just did. But now we go back up here and notice, and I didn't write this down, and you're probably thinking about it, we see that x cannot be 2. X cannot have the value -2 because, of course, if that were the case, the original equation would not be well defined. Again, we don't know what division by 0 is. So these could never be values of x. And of course, when you take calculus, the division by 0 is a fundamental approach where you talk about infinite limits. So we will have a lot of fun in calculus with division by 0 and its ramifications. So now we can see that this 3 is indeed legitimate because it doesn't have either of these values. So we could just write the 3 in the solution set. Now, what I wanted to do was to say, what if we just put everything on one side? So here I could do equivalently. And I just neglected to do what I did here, but I wrote the original equation with the value or the x term and the constant on the same side. So now when we subtract 34 from 10, we get a -24. So we could have done this, something like this. All right. So that would be like the ax plus the b. That is, the a is 8 and the b is -24, if we were thinking of that from the original equation. Let's see, I've got, remember right here when I wrote down just the basic linear equation? So you're thinking, how would that help? Well, now at this point, we could think of factoring the 8 because we know that the 24 is 3 times 8. So this would be 8 times x minus 3 equals 0. And now you're thinking, oh, this is what you did, and we'll talk about this, called the zero product. Okay, zero product. So the key here, and we do this a lot more, and I'll review this when we talk about quadratics. We do this a lot more when we have two factors that have variables. But notice here that when you look at this, you've got 8 times x minus 3 equals 0. So what does that imply? By zero product, it means at least one of these factors must be 0. Okay, well, the 8 can never be 0 because it's a constant. But this would say, equivalently, x minus 3 must be 0 by zero product. And this is a common theorem that's used. You often use this and you don't even think about it. And then, of course, x equals 3. And you get the same result. So when you reduce to the standard form, the result is the same. And in many cases, you do this because your goal is to use zero product. The zero product is so important. Obtaining that 0 to figure out where a particular expression has zeros and then where it changes sign is fundamental to doing real analysis. That is in pre-calculus and calculus. So I just want you to be aware that how you come about the actual solution, even though we're tending to do this more so when we have linear equations because it's so simple, you could certainly do this as you would have to do in other situations. So most students would refer to this as solution by factoring, in the sense that you obtain a 0 and then you factor and then apply the zero product. Okay, simple but important. And we'll use more of that later on, but I didn't want to miss an opportunity just to say something about it. Now, let's look at one more example. We want to do a word problem, but we'll have plenty of time for that. I want to just give a very simple example that doesn't require the LCD method, but just to remind you of some things. So again, we want to solve the equation. So here we've got x times 2x minus 5 equals 2x plus 2 times x minus 3. So again, we have x times 2x minus 5 equals 2x plus 2 times x minus 3. Now, what you notice about this is that when you apply the distributive law, you will get square terms or quadratic terms, but you can see that they're most likely going to absorb. Now, one thing that I may comment about when you're working with multiplication of expressions, factoring is often very useful because it makes the numbers smaller. Now what you can see here is that we have a 2x and a 2 here in this first factor, and you're thinking, well, I could factor the 2 and make the work a little bit simpler and just have x plus 1, and then as I continue with the problem, then multiply everything by 2. You don't have to do that. But let me just show you how you could do it. For instance, instead of a 2, if that were like a 100, okay, you're thinking that's kind of a larger number. I could go ahead and factor that and then pan it back through if I need. So let me just show you a simple technique. On the left-hand side, there's really nothing we can reduce. So we use the distributive law. So x times 2x is a 2x squared. Just any opportunity to do extra algebra is good. And then, of course, an x times a negative 5 gives us the 5x. Now, just to show factoring, I'm going to write this as 2 times x plus 1 times x minus 3, just to get some practice factoring. Now, this part here is just the distributive law. Notice what we have over here does not change, so we just copy it. We're like court reporters, as they say. And so now we multiply each of the terms by x. So x gets multiplied by x, that's an x squared. And -3 gets multiplied by x. And now they just get hit by 1, which is really simple. 1 times x is x, and 1 times -3 is -3. Now, when you look at this, it's very simple. So we've got 2x squared minus 5x equals 2, and then we can combine terms inside. We have an x squared, and then, of course, the minus 3x plus the x is a -2x minus a 3. And now, of course, there's not a 2 in this, so we won't make more fractions. So we have a 2x squared minus 5x equals 2x squared minus 4x. That is 2 times the -2x is a -4x, and then 2 times the -3 gives us a -6. Now, again, you didn't have to factor this here. You could have just distributed here, but I just want to show you how factoring can actually be very helpful, especially if you have common terms over here. So sometimes I will do additional steps, not because you have to do them, but I want to make you aware of certain techniques that can be very beneficial if we're trying to cut down on the amount of work. So again, when I show you a technique, it may just be to remind you of it, that you don't always want to overlook factoring, especially if it can make the problem simpler. Now, of course, the 2x squared terms are on either side of the equation, so they absorb. So this is true here. This particular situation does reduce, or this equation does reduce to linear, and we didn't think that at first, but we maybe thought it, a little bit by looking at it, but this does reduce to linear. So equivalently, now, of course, I've been a little bit sloppy. All of these are equivalent. That's how we solve equations. It's important to remind ourselves that everything is equivalent, because when we reduce the equation, when we write an equivalent equation, what we're doing is writing it in a form so we can determine a solution if one exists. So now we have minus 5x equals -4x minus 6. Now, of course, we're going to be lazy. If we add 5x to both sides, that gives us an x. And then, of course, if we add 6 to both sides, we just get a 6. Now, notice we don't have any problem here with the original equation. No values of x are kicked out, so to speak. There are no values of x that would render this particular equation undefined. It just might not be a solution. So now this would imply that we indeed have a unique solution set, which is 6. That is, we have one solution to this equation. Now, again, when you get to this point here, what I usually say is transposition. If you take, sometimes I'll just use arrows. If you add the 5x to both sides, it absorbs here, and the 5 minus the 4 just gives you the 1x. And then, of course, if you add 6 to both sides, transposing, you get the 6 here. So at this point, you might be saying, well, that's kind of complicated or whatever. You could say, well, what if I just multiplied the equation through by -1? All these negatives are just in the way. So you could say equivalently, 5x equals 4x plus 6. That is, multiply by -1. There is nothing that says you have to solve in a particular way. You just want to solve correctly. So one thing I could have done here is just multiply this equation by -1. That is, each term gets hit with a negative, and then we have this, and then like, well, that's really simple. So 4x from 5x is x, and then of course the 6 is already isolated for the same solution. So again, what I wanted to use in this particular example was just the algebra, a very simple equation, but utilizing some factoring and the distributive laws. They are very, very important. We often forget distributive laws when we get careless. And the thing about that is it's just easy to overlook. If we're multiplying numbers, a lot of times we forget about it, but we don't force ourselves to have to do it because we combine the numbers and then the distributive property kind of goes away. But what I want you to be familiar with is treat the variables just like numbers and apply any technique you like. If you want to get rid of negatives, multiply the entire equation by -1 and knock out as many negatives as you like. Here we had 3, we got rid of all 3. So don't worry about techniques that may be different from the way your colleague solves it. You have a classmate, they solve it this way. The key is using correct mathematics to get to a value that is legitimate. And then, of course, we don't have to worry about any values of x we get here because we know that this equation would not be violated by any x in the sense that it would always be defined. But we're thinking, you know, there aren't infinitely many solutions to this equation. Our ability to understand mathematics tells us that. And what we find is that the only solution to this equation is the real number 6. So just remember, solving equations is simply something that we do because many disciplines require the utilization of mathematics. By attempting to solve an equation, we may find that it has no solution. Attempting to solve an equation, we may find that it has a unique set of solutions. Maybe there is one solution, like 6. Maybe we solve the equation and we have 3 solutions. Or maybe we solve the equation and we have infinitely many. Now, another thing that's important to realize is that we may have a restricted parameter on the problem. For instance, the problem may ask us to solve in a particular interval of real numbers. And we have to make sure that the value that we come up with, or one of the values we come up with, actually lies in that particular interval. So depending on how the problem is stated, we may have to discard some of the values we get. If we're working a word problem and all of the values that make sense are non-negative, we would have to discard any values that were less than 0. It does not mean that the value did not solve the equation. It would mean that there would not be a realistic sense to use that value, especially if we were looking for the unknown to be a speed. Okay, speed in physics is non-negative. Now, velocities can carry a sign because they're vectors. So we have to remember that solving equations is very much a function of the type of problem that we're asked to compute. So just keep that in mind as we work through the algebra here, and as we get more refined in our techniques, we may have to be a little bit more specific on how we describe a particular solution set. Now, the last problem we want to do is again a useful problem, and the result is a linear equation. So here's the example. This is just a word problem. Now, in this particular example, we have, I'm going to set this up this way. I'll just say, we'll just give someone a name. We'll say that Alice works, in this case, 56 hours. In a week, in 1 week, say a particular week. And then she is paid time and a half. Time and a half, and no more dashes. Time and a half. Was that little eyelash there? Time and a half for hours in excess of 40. And in this particular problem, her paycheck, well, we're going to say we live in a no tax world. We'll just say, just to keep the problem simple, she is paid $600, in this case, $608. And here is the question: what is her hourly rate? So a very simple equation. There are times when I'll have a problem stated or it'll be typed or whatever, but sometimes it's nice just to write down the problem as if you're teaching it to someone. So again, we see that Alice has worked 56 hours and she gets time and a half for hours in excess of 40, and she's paid $608. What is the hourly rate? Well, again, you're thinking in your mind, we need an unknown, and the unknown is the hourly rate. So what we can do is set X equal to hourly rate. And we can use some factor trees here just to break down numbers. That's always a fun thing to do when you're doing algebra. So now we know that the hours in excess of 40 would be 16. So note, observe, 56 minus 40 will give us 16. So these are what we call the overtime hours. So we have overtime hours. So now we simply apply the hours times the hourly rate, and then time and a half gives us 1.5 or 3/2. So this implies, in this case, 40 hours times X plus 16 hours. And I put a little dot here just for purposes of emphasis, 3/2 X equals 608. So again, we have the number of hours times the rate. So for those 40 hours, she gets her hourly rate. But for these 16 hours, she gets time and a half. So she gets 50% more of the hourly rate. So again, think of this as the rate for overtime and the regular rate, so to speak. Sometimes a problem will be stated, what is the regular rate? Okay, so I paraphrased a little bit here, but it means the same thing. So now when we look at this, what we want to do is clear the denominators, but how simple. We can see that the 2 will just absorb into the 16 and we're done with that. So equivalently, 40X plus, and so if you like, just to make it clear, just write this 2 times 8 times 3 over 2 x equals 608. And we'll factor the 608 with a factor tree. So now notice the 2's absorb. So now if we look at this, we've got an 8 times a 5x. I'm just going to write the 40 as an 8 times 5. And then here we have an 8 times 3x. No need to add these yet. And so what we want to do is break this down. Let's just go ahead and do a little factor tree here. It's always good to practice this, especially when we do rational zeros theorem, when we get into theory of equations. So let's just go ahead and break down by 2. So 2, so we get, in this case, what, a 3, a 0, and a 4. Let's do another 2. So we get what, a 1, a 5, and a 2. And do another 2. So of course we'll get what, a 7 and what, a 6. Now, what we're seeing here, when we look at this, we still may need to break down a little bit more, but notice here's an 8 right here. And we've got an 8 in each of these. So at least for now, I'll just do a little sidebar. This will be 8 times a 76. So we've got a new factorization for 608. So we'll write it as 8 times 76. Now what we can do is use our boxes. Now all the 8's absorb. And now when we look at this, we can say, well, the 5x plus the 3x is an 8x. And then we're left with a 76. Now at this point, again, you want to look at this and say, well, can we keep going here? We've got more 2's here. So let's keep going. So we have a 2. So that's will give us, well, and when we divide here, we get a 3 and then a 16, that's an 8. And then we get another 2. So now we get a 1, and then we get what, 18, that gives us a 9. So now we're like, okay, we're good. So that gives us a 4 times a 19. So we get what, 4 times 2 times x equals 4 times 19. This is what we call symbolic calculation. This is a new approach to teaching math, and it's kind of become part of how the little people are taught, where they're shown how to break down numbers and let the numbers do the work for them. And you've been doing this. Sometimes I think you just overlook it, but now what we can see is the 4's absorb. And then we're thinking, well, are we going to do what we did before? Let's just practice what we did before, just for fun. Use the zero product. So we get 2x minus 19 equals 0, just for fun. Basically, it's just 19 divided by 2. So now factor the 2, and we just get 19 over 2 equals 0. So of course, by zero product, x would equal 19 over 2. Equivalently, x equal 19 over 2. And of course, that would be 9 1/2. Or if you wanted to write this in terms of dollars and cents, that would be $9.50. So when you look at this particular problem, we would say now the hourly rate is $9.50. So the key here, and what I want to show you, is when you think about solving equations, especially when you get to polynomial equations, you get to logarithmic, exponential, and then as you get into pre-calculus, even at the end of this course, when we talk about matrices and solving linear equations in systems, we have to have some method that is reliable. And we want to do it systematically. Now, of course, when you get to pre-calculus and you study trigonometry, you will apply the same techniques, but we have to be able to break things down into pieces. And when you think about a very simple linear equation and writing it in a standard form and then factoring and using zero product, you tend to position yourself for better work as problems become more complicated, because what we're finding and what you'll see in this class is that factoring will be an essential technique throughout the class, because it will allow us to apply that zero product that is so important in solving equations. So again, one thing I want you to practice is the following. Let the numbers break down and give you the answers that you're looking for. You're thinking, oh, I could just, dump all of this into a calculator and figure out, and there's absolutely nothing wrong with that. But what I want to do is take the time to show you how you can let the numbers do the work for you. And especially if some of you become tutors, the idea is if you use your factor tree, you can easily divide by prime numbers and break down the number very easily. And of course, when we try to factor quadratics, we have to always look at the numbers and see what they tell us to see if we can actually factor an integer polynomial, over the rationals, which would give us a integer factorization. We'll say more about that in the next lecture. So as you're working with these problems, some may be very simple, albeit, but practice the technique of creating the LCD. If it easily absorbs like it did here, then fine. We're happy for that. The statement of the problem allowed for that. But in other instances, you don't have that, and then you just let the algebra diminish the equation and not necessarily diminish, but transform, that's a better word, transform the equation into a simpler form. The simple form allows us, for instance, when we get to this point, to easily say what the value of x is. So again, just remember, the process of solving an equation is writing it in a form so you can determine the value of the unknown. The original equation has the same information, but we look at it and say, well, I'm not really sure what the answer is. I've got to work on it. So the key is this. We don't want to think that every equation we solve is something we just kind of think about, or we intuit, or we do trial and error. Trial and error is certainly not a bad way to look at solving certain equations. But with most of the equations that we work with in this course, we want to be able to utilize the number theory and the algebraic properties to break the equation down to a simpler form that will allow us to solve for the value of the unknown. Okay, so enjoy these linear equations. We're done.